This video, I'm using artificial intelligence text-to-speech trained with my very own voice. There was a day, I randomly searching online, and I can't really find it again, but there are two kinds of classical supersonic airfoil, which are circular arc airfoil and wedge or double wedge airfoil, and interestingly, wedge airfoil has lower supersonic drags than circular arc airfoil. Also, I want a better supersonic airfoil design, so I start this project. Talking about supersonic, the most important thing is wave drag. To minimize wave drag, the basic idea is shaping its cross-sectional area close to Cirrus hawk body, which is minimum wave drag. Here is airfoil cross-section of circular arc and wedge comparing the Cirrus hawk body. You can find that none of it looks shaped well. So here's an airfoil that I designed it to be close to Cirrus hawk body, and I can scale it to be thickness whatever I need. It is what it looks like. Also, I gonna use airfoil point file, so if you want to try it. I asked ChatGPT for any idea of this airfoil's name. So this gonna be wave trim foil with thickness following behind. To figure out its performance, I ran CFD analysis of these airfoils at rate 1,835,020 and Mach 1.30. I run it up to 30 degrees angle of attack, but in high angle of attack flow separation makes it not steady, so it's not really accurate at high angle of attack. With its CL graph didn't looks very interesting. And CL at supersonic, even in this case of 2D airfoil, is very low compared to subsonic. CDCL graph, which you can find, is that wedge airfoil is really performing better than circular arc, even having the lowest drag. My wave trim foil design is somewhere between circular arc and wedge. And here is pitch movement of 25 chord line and aerodynamic center. Not very interesting. I also CFD analysis with different thickness. Clearly you can find that thickness is the most important factor of supersonic drag, because thickness directly impacts wave drags. CDCL graph looks like drags at zero angle of attack are kind like an offset of the curve, and also heavily affect the maximum lift and drag ratio. So in supersonic you always should be trying to make your airfoil as thin as possible. Last, analysis of these airfoils, now lift drag from subsonic to supersonic range. Actually, my wave trim foil performs best at transonic from roughly Mach 1 to Mach 1 to Mach 115. For any higher Mach number, wedge appears to be better. And in subsonic speed, circular arc performs best and wedge is the worst. Looks like you can't take both of it, and my wave trim foil is always in the middle. So that's it for this project. I designed a supersonic airfoil that performed quite decent, and there will be a link to download this foil if you need it. But that doesn't mean there is nothing left to do. I think that there is still lots of further work I can do. For example, wave trim foil is just an airfoil that I shaped to reduce wave drag, and it is hard to do more design based on it because there isn't some kind of way to accurately describe shape. I am already working at use of function to describe shapes, and based on that I can easily extend this design and can able to use some factors to determine a specific shape, just like the NSCS series airfoil. So that's it for this video. If like, hit that like button, and if you're interested in the further project, then subscribe this channel. See you next time.